Okay, so we are in chapter 5, and we're talking about cloud-based software design. And we're now talking about like how, from the perspective of there's two perspectives that we have to have when we think about this. One is the perspective of the consumer, the person who requests cloud services, and the person who creates the cloud services. So from the perspective of the creator of the cloud services, he may have what's called a multi-tenant database, which means that he has many customers on the same database, but each one is isolated from the other, so that they all have access to from their perspective, their own database. But really, it's one database or one table even with multiple clients on it, and they access, they remotely access the data, and they only can access their own data. In such a case, we have a single database schema, but which is shared by all the users. And here it says items in the database are tagged with a tenant identifier representing a company that has stored the data. Database access software uses this identifier to prevent logical isolation. They call it logical isolation because it's really not isolated physically. It's all on the same table, which means that users seem to be working with their own database. So here is like a picture of this. And you see, here's tenant number 516, and here he is again, and he's got different items in his database. Notice that the same key may be multiple times because it's a different tenant. So the effective key, in other words, from the perspective of the tenant, his key is 100, and he doesn't see these other ones because we're gonna always filter by his tenant ID. So from our perspective as the creator of the database, the effective key is the combination of these two keys. And here's the item and the supplier and the data was ordered, for example. Okay. So the advantages of multi-tenant databases as compared to a database, individual databases for each client. Well, it allows the creator, it allows the provider to use his resources more effectively. He doesn't have to have so many databases. It's easy, so many tables. It's easier to maintain. Right. He can have the software optimized in some way to make things run faster by having fewer tables. But we have to remember to have security. In other words, we don't want to have one client accessing the data of another client. So, but since we're already getting involved with security, we're likely to have a more secure database at the end of the day, because we're thinking about security much more. Also, there's only a single copy of the database software to be patched if we have some kind of vulnerabilities discovered. In other words, when their patches come out, it's easier for us to maintain because we have fewer instances of the database. And it's easier to update rather than having multiple updates. So there's certain conveniences of having one system, but there are certain disadvantages. And the main one is that customers must all use the same database schema, which means that they have to have the same fields. So that limits our ability to have different kinds of databases. And theoretically, there could be somehow data leaking from one customer to another. This is not really going to happen, but theoretically it could. And if there would be a breach of the database, it would affect everybody, as opposed to the hacker having to hack each individual server. Okay. It's also more complex to maintain, because notice how the keys were, multi-keys. We had to have 2 keys to find things a little bit more complex. But we can handle complexity. But there's more likely to be bugs. But we may want to have customizations for our, remember what SAA, software as a service. So, well, we were still in that general topic of software as a service. What do we mean by software as a service, actually? Software as a service means that it's like totally different from the idea of a person ordering a database from a cloud provider. Instead of ordering a database from a cloud provider, he's asking for a service from a cloud provider, like a service that finds that tells me about flights, airplane flights. That would be a service. He's not interested in programming himself. He wants a service. He wants to be able to query a server and get data back from it, but not create his own databases. I think we saw there was a diagram before. Maybe I'll just remind us of that. Here's a diagram. Well, that's a good diagram. This shows you that the clients want services can get services from the cloud. Now, there's directly the service as opposed to getting us a database. Wait, where do I think there was another diagram. Sorry. No, I don't see it there. Maybe it's going to come up. So we may have customizations for these services. For example, authentication. A business may say, we have our own password system for our workers, and we want to use that on your system as opposed to your own password protection. So that means we have to adapt to their password scheme. Branding. So they may want their name, in the service. Business rules. They may have their own rules about, like, when there's a sale or how workflows happen. And they may want to extend the data model. We're going to talk about that. They may want to have more data than the normal system wants. And we as the service provider may have to change may have to be flexible enough to provide these different requests. They may want to be able to find their own access control model. In other words, that various users can have different levels of access. And we have to accommodate that also as a service provider. So we're going to have different profiles for different companies. Company 1 will have its profile, and company 6 will have a different profile. And the users of each of these companies will access the service, which is in the center here, but via a different profile. So this is kind of like a layered approach. In other words, we have our basic service, and then that goes through. We have to have to build in automatically, let's say a default profile, and then we can modify profiles for different companies. There'll always be a profile through which you're accessing, and there's another layer of software through which you're accessing the service. Now, as far as the schema, here is how are we going to give them more information? For example, let's say company 516, here's 516. Let's say he wants extra extended fields. He wants extra information about his widget or his object or his thing. So we may have extension 1, extension 2, extension 3. Now, the problem with this is that we're going to have all these extensions for every company, but it could be that company 973 doesn't ever use any of these extensions. Or maybe he has his own extension. Maybe he only uses extension 3, and 516 only uses extension 2, and 632 only uses extension number 1. So it comes out that there's a lot of extra fields in our table that are never used by most people, because especially if we have hundreds of companies. So there's a problem with just extending our database. I mean, that's why we would normally have a different schema, but if we're sharing, we're not able to have a different schema. So how can we overcome that problem? Well, here they're just pointing out some of the problems. This is what I said. You could add additional columns, which is what we did. However, it's difficult to know how many extra columns. Maybe customers won't have what they want. If you cater for customers who need a lot of extra columns, you'll find that most customers don't use them. So you have a lot of wasted space in your database. Different customers are likely to need different types of columns. Some customers may have strings and others want integers. You could get around this by maintaining everything as a string, because remember, you can represent a number as a string. However, this means that either you or your customer will have to provide conversion software to create items of the correct type. In other words, at some point, you have to convert that string into an int. So this is a certain problem, what we're going to talk about. So what about extending a database using tables? An alternative approach to database extensions is to allow customers to add any number of additional fields and to define the names and values of those fields. So we're going to show that we're going to add more tables without changing the schema. We're just going to add another table. So let's just look at the picture right away, and let's understand this picture. Interesting picture, actually. Welcome to everybody who came. So, for example, let's look at tenant number 516. He's my favorite. Now, he has ID number 100. And there's only one extension field here. Notice that. There's only one extension no matter how many I want or which companies I want. So what we'll do is like this. When we see that he's extension 1, 2, 3, these are all unique. These are all unique. So extension 1, 2, 3 means go to this field and find 1, 2, 3. Now, the extension, since we are tenant number 516, we are going to also look at this field names and see that 516 has always 3 extensions. For this field, this table will be a table of all the extensions for all the different companies, and they'll be grouped by companies. In other words, 516, he only has 3 extensions. They're all here. They're not going to be scattered throughout this table. They're all right here. And then 632 has these extensions, just 2, and 973 has 1 extension. So when I come and I see that this is tenant 516, and so then I know that he's going to have 3 extension fields, and they're going to be of type string, int, and bool. And their meaning is location, weight, and fragile. And well, I'm going to come over here, and I'm going to see, oh, here is record 1, 2, 3. And I know that the first one will be the location. It's on shelf number, it's on row A17, shelf number S6. And I know the second field is the weight. It's 4 units of weight. And I know that the next field is whether it's fragile or not. False, it's not fragile. So I have these three values as defined by this here. And I know that they're all related to widget 1, which is owned by tenant 516. And therefore, but it's basically the same principle that we always use in all of our courses in operating systems and in here, which is abstraction. In other words, this is, instead of putting the actual field here, we put an abstraction, a pointer to the field. And then we can have as many extensions as we want. It could be that one has 3 extensions and one only has, and one company like 973 only has 1 extension, but everybody has only 1 extra column, the extension column. And therefore our table doesn't have to get arbitrarily large. And this is all designed for having multiple clients using the same main database table. Any questions on that?
How does table 2 connect to table 3? Like, how does it? Like, how do you know that they're connected?
Yeah, right. The arrow is not drawn here. The arrow is not drawn here, but table 2 is connected to table. In other words, when I do a query, I will. In other words, I'll also query this table. I'll query table 2, and I'll search for T516. And I'll get these 3, and I'll do a loop on these 3 things, and I'll loop through this table for each result that I got over here. And I know the first result is the first field, the second, and the third. I mean, that's the basic idea. In other words, it's not shown here that all the queries. You'd have to do a query to this table and then a query to this table. The yeah. Okay. So that's just a solution that's a better solution for this. This is a worse version. Okay. Oh, so wait, let's just describe that. So that's what it said. This chart, this slide is just describing what we just saw. The names and types of these values are held in a separate table. That's that table that Chevy was asking about. Access using the tenant identification number. Unfortunately, using tables in this way adds complexity to the database. In other words, it's going to be more complicated to do a query, and we're going to have more tables. Extra tables must be managed and information from them integrated into the database. So fine, it's more complicated. Yeah, but that's, as programmers, we live for complication. Information from all customers, so data security. So database security. Information from all customers is stored in the same database in a multi-tenant system. So software bug or attack could lead to a breach of data for everybody. So multi-level access control. So we're going to have multi-level access control, which means, well, I mean, this is not really related to the first point, but we're also going to have 2 levels of security, right? Because we're going to have, first of all, the organization is going to have its security. In other words, in order to get into the database at all, if you're, for organization number 1, he has to have a password. Everybody from organization 1 has to have organization 1 password to get into the section of the database for organization 1. But then individual users from organization 1 have to have their own parts of their own passwords for the parts of the database that they're allowed to use, and to identify themselves. So that's what it means by multi-level access control. The organizational level and the individual level. I'm just trying to think of an example. Like, for example, if I want to look at my pay slip from my work, I go to a company, I go to an external company, not Machon Lev, which I put in my password, and my organization number. Or somehow I guess in the URL actually is the organizational number, which that I'm Machon Lev. And then my user ID and my password. And my user ID is actually like is like, could be like a number like 200. Even though there's thousands of people there, somehow I got 200 because I'm 200 at Machon Lev. So my ID is local. That's what we talked about before. The service has to be customized for the authentication that the company wants. Like at Machon Lev, for everything that I want to see about my pay slips and all my pay things are always I'm number 200, whether the service is coming from company A or company B or company C. So company A, B, and C all have to integrate my ID number, my username essentially, into their system, but they may have already somebody with number 300 with number 200. So so really I'm ready 200, but they're changing that into some other number internally. And they know that I'm 200 from Machon Lev, and that creates the uniqueness. So anyway, that sort of relates to the idea of multi. In other words, I have an individual access to a service through a company. You need to have organizational level access control to ensure that any database operations only act on the organization's data. Right. In other words, I can't affect the, if I mark that I came to work this day, it shouldn't be that I mark on somebody else, some other company. And also I shouldn't be as some other worker at my company. Encryption of data on a multi-tenant. So here he says, you could also, another thing you should do is encrypt your data in your tables so that the corporations have the feeling that it's more secure. Fine. Okay. So now there's the alternatives. Like that was multi-tenant. Now we're talking about a much simpler thing, which is multi-instance databases, where you have actually replicated, several databases. You have, through that replicated, you have different databases on your system. And you have, each time a new client comes, you create him his own database. So in other words, when I go in to look at my pay slip of that company and that service provider, they created me for Machon Lev, for my company, its own database with its own everything. They're conceptually simpler than multi-tenant ones, right? They're much less to talk about. You just create another database, and then you can have whatever you want. You avoid some of those security concerns like data leakage from one organization to another, because everybody has their own database. I have no access to that. Even if I ruin my database, if I somehow ruin my database, I'm not going to ruin the other guy's database. Right. I mean, I just want to make that clear. And now I can I maybe somehow could delete a table. My organization maybe could delete it. Well, if it's a service, I shouldn't be able to delete tables because I'm really just, remember when it's service, then I'm just interested in getting the service. I just want to give my workers the ability to see their pay slips. So I'm not creating databases. That's their problem. So they shouldn't be able to delete anything. Okay. There are two types of multi-instance systems. So, right. One is the virtual machine-based multi-instance systems, which means, we talked about virtual machines, which means you have some kind of hypervisor on top of the hardware, and then you have on one machine several different operating systems or several different complete systems. See, why do we have several different operating? It could be several of the same operating systems. It could be several instances of Windows on the same hardware. Why would we do that? Now, as we talked about before, wanting to have like virtual machines so that you can have different operating systems. So what if you want actually the same operating system multiple times? Well, the answer is to provide my clients with a complete separation of their software from somebody else's software. If one if one database gets corrupted or jams the operating system and the whole system has to be rebooted, it'll only affect that company for whom the database got corrupted or for whom the operating system got destroyed, and it won't affect the other companies that I'm providing service to. So by having this sort of virtual machines, complete separation, I have actual different operating systems, then different instances of the operating system on one machine. If one goes down, it's not going to affect the other. If one gets attacked or hacked, it's not going to affect the other. I give complete separation. So that would be one way of doing things with this virtual machine. Each customer runs its own virtual machine, its own operating system. All users from the same customer may access this, right? But if all people from the same corporation that have registered to this service are going to obviously use the same database. The second method is container-based, which we talked about. We saw a movie about how you make a container, and I hope that took away some of the confusion or obscurity regarding what a container is. Container is basically the idea that on one operating system, I write a series of scripts or commands or definitions in the system, such that each user is not affected by the other users. For example, I limit the amount of CPU use that one container can have. I say each container can only use, this amount of CPU time, or this amount of percent of CPU time. So then, even if one container gets attacked with a DOS attack, a denial of service or something that causes him to use a ton of CPU and therefore not provide service anymore, right? You're familiar with a denial of service attack. It's where you request something from a server so many times that the server is swamped and can't provide anybody with service. So if I have multiple services on one machine, but they're in different containers, then a denial of service attack may swamp one container, but it won't affect the other containers, and therefore the other services will work, even though they're all in the same operating system, because I have isolated the containers, and that's what this video that we saw explains how to do. There are multiple instance systems where each user has an isolated version of the software. In other words, it's the same software, but I have an isolated version of it, and an isolated version of the database, which I only can access in my container, and my container only gives me a limited access to the database. So it's kind of like a virtual machine, as opposed to the first option, which is an actual virtual machine. Yeah, so those are just to understand there are two different approaches to having multiple instances. And that's all in opposition to the tenant idea of having tenant databases. Advantages of multiple instance databases, which I sort of said some of them. Each instance of the software can be tailored and adapted to the customer's needs. In other words, I can have different schemas, different database schemas for each customer. And it is straightforward to transfer data from a customer database to the product database. Because I know, well, I'm not sure what he means by product database. I think it might, I guess the point is I know how to get the data out of the database for this particular client, because it's very straightforward. I don't have to check lots of different tables to figure out which is his data. Security. Each customer has their own database, so there's no possibility of data leakage, because I have my database, or even if it gets hacked, it doesn't have anything to do with yours. And how would I even access your database? Scalability. Instances of the system can be scaled according to the needs of the individual. For example, some customers may require more powerful service than others. So since they're all on different databases, I can give him a more powerful, I can put him on a different server. I can have, I can have the most powerful server, the medium server, and the weakest server, and then I can put some clients on each, and depending on how much they want to spend. Resilience of a software failure occurs. This will probably only affect a single customer. In other words, if, like I mentioned that if one server gets hacked or fails for whatever reason, it won't affect the others. Costs. But it's more expensive to use multi-instance systems because of the cost of renting many virtual machines in the cloud. Well, that's true of virtual machines, but not of containers. In other words, if I'm providing a service, if I'm the company that's providing the payslip service to Machon Lev, so I also need servers, and I need to buy them from cloud. And if I'm going to, I actually pay for each virtual machine that I want from the cloud provider. So it's going to cost me more, and therefore I have to charge Machon Lev more if I have to, if I'm going to implement my system on multiple servers, on multiple databases. And also, once I requested it, maybe nobody's using their virtual machine for a long time, and all that, and I can't turn it off because maybe tomorrow somebody will request. I mean, I don't know when the request will come, so I've got to leave the virtual machine on all the time. But if I had only one virtual machine, then I can like sort of balance. Like chances are that if I have more companies working on one machine, then it'll probably be a constant load, and that's more efficient and therefore cheaper. Update management. It's also easier to update if I have fewer machines. I don't have to update them all. Well, that seems to be less of a problem. It's only if I'm updating with my own software, right? If I change my software, then I've got to deploy my software to all the different virtual machines. Okay, so in order to make a decision about what type of design I want, whether I want virtual machines or containers, or I don't want either, I want to have tenants, I'll have to ask myself, well, I'll have to ask myself this question: should the software use a multi-tenant? Should it use this? I have to decide. I have to answer that question. What are the software scalability and resilience requirements? In other words, will I need to make my software larger or smaller? For handling larger clients, larger numbers of people. Should the software structure be monolithic or service oriented? So these are big questions. Like we're talking about service oriented, where the software itself is service oriented. In other words, I have different servers providing. Now let's go back. In other words, when I'm creating that payslip company and that payslip software, I have lots of different functions that are required to create my payslip viewing and updating company service. And to provide my service, I need to use other people's services. So do I want to use other people's services, or do I want to write the software myself? Okay. Right. In other words, that's the way software is done a lot of times nowadays, where there are all these people out there, millions of programmers out there in the world, and millions of companies providing little tiny services. And I want to write a new piece of software. I'm going to take like Legos. I'm going to take a service from him and a service from him, and I'm going to make an API request to get this information from that service, and another API request to get from some other service. And I have to learn the APIs, API just means how do I communicate with that service? And we talked about this. I can send either a JSON or an XML request over the internet and get the data back. And all the different services that I want, I piece it all together and I make a new service now. That's a way of programming. And all of these things will help me decide what cloud platform should be used for development and delivery. Questions to ask when choosing a database organization. That's how am I going to organize my database? So target customers. Do the customers require different database schemas and database personalization? In other words, am I getting totally different databases all the time? Then it might be better not to have a tenant-based thing. If they're mostly similar, then maybe I can use tenants. Do customers have security concerns about database sharing? If so, use multi-instance databases. In other words, if customers are very, very nervous about security, then maybe they're not going to like to hear that I'm using tenants. Transaction requirements. Is it critical that your product supports ACID transactions where the data is guaranteed to be consistent at all times? So ACID transactions is a concept of basic. ACID is an acronym for autonomy, consistency, I don't remember exactly independence, but basically the idea is that forget exactly what they all stand for, but the idea of an ACID transaction is that if I, for example, take money out of my account and put it into your account, that transaction shouldn't get corrupted in the middle. It should be atomic. In other words, I should be able to take out my money and put in your money, and nobody will stop me in the middle, and then it won't fully execute. It has to fully execute. Once it's started, it has to complete, which means it also has to recover from failure. No, it can't fail, essentially. That's what an ACID transaction is. Because you ever wonder how is it that your bank account always has the right numbers in it? Like there's never a database error, there's never anything. So there's a lot of work done to maintain that. And one of them is by having multiple redundancies of data. Anyway, if it's critical that you support transactions like that, like for example, you're in a bank. A transaction, by the way, is the whole thing. The taking of the money from one and putting it in the other. And and changing the relevant numbers, obviously. Where the data is guaranteed to be consistent at all times. If so, use multi-tenant database or VM-based multi-instance databases. In other words, well, these are very different. You say, what do you mean use either these or these? And don't use what? Don't use containers. Don't use containers because containers, interesting. Why? Containers are ultimately still the same operating system. So there could, if a container is written, I'm not sure I understand why not to use containers, why you should use only a multi-tenant or a VM. Not sure why. But I do see that you would want to have the, ideally, you'd want to have the transactions on the same system. Anyway, database size and connectivity. How large is the typical database used by the customer? How many relationships are there between database items? There's how many jumps do you have to get all the information from your tables? A multi-tenant model is usually best for very large databases, as you can focus efforts on optimizing performance. If you have very large databases, then you want to do a lot of tricky stuff with your database to make it faster. And that may be easier if it's all one database and have to duplicate it on many different databases. Database interoperability. Will customers wish to transfer information from existing databases? In other words, maybe they have their own databases and they have their own payslip information on their own servers, and they need to upload it onto mine so that I have a complete history, so that they can, so the workers can now access the new service and get all their old information. So that would be called transferring information from existing databases. What are the differences in schemas between these and a possible multi-tenant database? In other words, maybe their database doesn't fit, their old database doesn't fit to our multi-tenant one, and then I probably need to have a custom database, and then I maybe don't want to have tenant architecture. What software support will they expect of it? If customers have many different schemas, and a multi-instance database should be used and not a tenant one. System structure. Are you using a service-oriented architecture for your system? Can customers Can customer databases be split into sets of individual service databases? If so, use containerized multi-instance databases. In other words, if your architecture is designed to be compartmentalized, then you probably should compartmentalize your databases too. Okay. Scalability and resilience. So scalability is, we've talked about before, I think, the ability of a system to adapt to higher demands. In other words, if I know there's going to be more load on the system, can I increase the system? Can I make it faster? And resilience is the ability of the system to continue functioning if some of its systems, subsystems fail or are attacked. In other words, can it keep, like a car, if the air conditioning breaks, it doesn't kill the whole car. The car can keep working. So that would be resilience. Can the system continue working even if certain parts of it fail? Scalability is the ability to get more power when I need. So how do you achieve scalability? So usually what we do is something called scaling out as opposed to scaling up. Scaling out means I have more servers. I just add more servers. Will that help? In other words, if it doesn't help, then my system isn't scalable. But usually it will help, and then my system is scalable. But I have to make my system such that it can handle, that it can work with multiple servers. If my system is designed is hard coded to work with only one server, then it's not scale outable. But it is scale upable, which is to transfer my system into a more powerful server. Scaling up just means take a better server, the faster CPU or more memory. That would be scaling up. But so the system also needs to be able to be written in a way that takes advantage of that scale up. For example, if it's written for a 32-bit architecture and I put it on a 64-bit architecture, it may just only use 32 of the bits and not use the rest of the bits. It has to be written for a 64-bit architecture. In cloud-based systems, scaling out rather than scaling up is the normal approach used, right? You're just going to add more servers. You're not going to increase the power of your servers in general, because then you can also turn them off when you don't need that power anymore. It's more simple. Your software has to be organized so that individual software components can be replicated and run in parallel. In other words, you have to have everything parallelizable. It has to be able to be run, which means you're going to have some kind of load balancer or some kind of, you're not going to directly access any service, but you're going to go to a sort of a policeman and say, I want this service, or a maitre d'. And then the maitre d' will tell you which particular server to go to get your service. Like a maitre d' in a restaurant, you go to, you say, I want a table, and he chooses which table you get based on, what's available. So you'll have to have for every service a kind of maitre d' who you always approach. And sometimes there's only one server available, and then he'll send you there, or one server existing at all, and he'll send you there. But there might be multiple ones, and then he'll send every person to a different server. To achieve resilience, you need to be able to restart your software quickly after a hardware-software failure, right? As it has to be that you can turn, which means essentially that when you change configurations in your server, how you configure the server, those configurations have to be recorded in configuration files so that when you restart, those changes will be read by the configuration files and will automatically update your server the way it was before, as opposed to making on-the-fly changes. If you make on-the-fly changes to your server, now all of a sudden you need to turn it on and off. All of a sudden it doesn't work the same way. You need to make all those on-the-fly changes again. So that's for example, that would be one thing you'd need to have. You need to have a system for maintaining all the alterations that you've done to your server whenever you turn the server off. I mean, this is standard in modern operating systems. Using a standby system to provide resilience. So here's an idea. you can have your active system over here, and then have a whole complete system on standby that you don't use, but only you use it when the active system fails. And then you have to mirror the database, which means every time there's a change in this in database 1, you'll have to also change database 2. And you'll have to have some kind of system monitor going on. Now, everybody's coming into active system. But what's a system monitor over here? That's another policeman kind of who's observing the active system and constantly testing it and making sure it's still active. And if he detects that it's failed, then he's going to have this standby server become the active server. In other words, for example, if everyone's going to IP number, 11222334, then this one will now get that IP. Location B will now get that IP, so that everybody will come here. That would be a way of switching to the other server if this one fails. Resilience. So that's what we just sort of said. Resilience relies on redundancy. See, I have a redundant system over here. Replicas of the software and database are maintained in different locations. Database updates are mirrored so that the standby database is a working copy of the operational database. System monitor continually checks, this is what we said, the system status. It can switch to the standby system automatically if the operational system fails. You should use redundant virtual servers that are not hosted on the same physical computer. Because if the computer fails and you have a redundant system, which is actually a virtual machine on the same server, then you didn't achieve anything. You need to specify, if you're on the cloud, then you need to specify, I want this on different hardware. And even in a different data center. One I want in Kentucky and one I want in North Carolina. I don't want them on the same data centers because maybe one will get attacked by a bomb and get blown up. And then even if I have on different hardware, I lost my service. So you need to have different hardware, really different locations. If a physical server fails, or if there's a wider center failure, then operation can be switched automatically to software copies which are elsewhere. Okay, system structure. So first of all, you can use object-oriented design. Secondly, you can have a monolithic system, which where even if you use multiple servers, it could be a monolithic design in the sense that they're not well, they're I don't know why it's a little bit weird. They call this a monolithic system, but with large software components on different servers. So this is like that the system itself is running on many servers, but it's not service oriented. In other words, I'm not making service requests. I'm not sure exactly how the communication is done between the servers. This is really what we're talking about more in this course, is the service-oriented approach, where the system is decomposed into fine-grained stateless services. In other words, I have it on different servers, and I can make a request for a particular service. I need a certain piece of data or a certain piece of information, and I make the request and I get back the information. I guess the other alternative is that instead of it being a small request, it's also a request, but it's a larger request. It's like, and therefore it's not called services so much. That's the only difference I can think of, because if it's normally you think of monolithic design having to be on one server. How could it be on if it's on multiple servers, then you have components. It's not really monolithic. So I guess what they're trying to say is that you could have large components, and then that's kind of like monolithic. Because each service is stateless, each service is independent and can be replicated, distributed, and migrated. In other words, What do I mean by stateless? No, it's not like he has to keep track. On the third time you make this request, then I give you different information. No, whenever you make this request, you give me all the information you need. It's not like I have to remember what your previous request is. If your previous request, it's not like first I give you, first I tell you my name. Then you say, I got your name. Then I say, okay, now I want, this information from the database. Then I give you that information. Then I say, I want this other database. And all the time he's remembering what your name is so that he's getting from the right database. That would be not stateless. Stateless means every time I make a request, I give you all the information and you don't have to remember anything. You don't have to remember what state you're in. I just always give you all the information. So once you have that complete independence, then it's much easier to have multiple systems. I can 1 minute request from one server and the next second request from a different server, and I'll get the right information because everything is stateless. Everything, I'm giving it all the information all the time. This is suitable for cloud-based software with services deployed in containers. Okay. Cloud platform. Cloud platforms include general. So what kinds of cloud platforms are there? So there's general purpose clouds such as Amazon Web, and there are also specific, which is, the standard one nowadays, I think, Amazon Web. There's also Microsoft, and there's also Azure, it's called, and there's also Google has one. I don't remember the name of Google. Maybe it's just Google. But these are standard ones. But then there's also something which I never heard of, which is the SAP Cloud Platform, which apparently is specific for certain types of services and applications. As you wouldn't have this for, you can't just get a standard server for them. You might be able to only get certain things. Like, for example, you could imagine a database cloud where all you can get is database. So you can't get any server you want. You can only get a database server, but they provide you with the databases. So you could go to a cloud platform for databases. And here it says there are also smaller national providers that provide more limited service, but who may be willing to adapt their services to these different customers. Like Amazon is not going to change their whole system because you made a request, because they're servicing millions of people. But if you go to a smaller cloud platform, they may be willing to change something, the way they do things, or provide you with a new feature because they don't have so many clients and they were looking for every new client. Also, there may be national security issues. Like if you're working for the federal government, you may have to use the federal government's cloud platform and not Amazon's. There is no best platform, and you should choose a cloud provider based on your background and experience. In other words, if you've used one in the past, probably it's a good idea to keep using it. The type of product you are developing and the expectations for every customer. Yeah, if somebody's always been using Amazon, they're probably going to want to keep using Amazon. And then if they hire somebody from Google, he's going to try to argue, no, Google is better. And the real reason he's arguing Google is better is because he just knows Google and he'd rather keep using it. You need to consider both technical issues and business issues when choosing a cloud platform. In other words, business issues might be, like I said before, customization. Will they customize for you? Can they support your own passwords, business-wide passwords, as opposed to their own passwords? Technical issues in cloud performance choice. You have to know at what level of resilience you want, what level of load you think you'll have. Do they support the services that you want? Maybe you don't want just a server from them. Maybe you want a service from them. And then do they have that service? What kind of privacy and data protection do they provide? And there are business issues, which is like, for example, cost, developer experience. If everybody knows Amazon, it's not necessarily a good idea to switch to Google. Customer target, I'm not sure what they mean by that, but you have to think of who your customers are. Portability, service level agreements. What kind of agreements can they give you? Can they guarantee you service for a certain amount of time? Okay, key points. The cloud is made up of a large number of virtual servers that you can rent for your own use. If you want the server, you and your customers access these servers remotely over the internet and pay for the amount of server time you use. Right. And we said also that you don't have to, where you have just a whole server, you could have a service request. Virtualization is a technology that allows multiple server instances to be run on the same physical computer. Right, we talked about virtual machines. This means that you can create isolated instances of your software for development on the cloud. Virtual machines are physical server replicas on which you run your own operating system, technology stack, and applications. Containers are different. They are lightweight virtualization technology that allow rapid replication and deployment of virtual servers. In other words, it's a virtual server, but not a separate virtual machine. It's on the same operating system. All containers run on the same operating system. Docker is currently the most widely used container technology, which I skipped. I did not explain how Docker has worked, but because the explanation in the book is not sufficient to actually let you do anything. But that is the most widely used container technology. Notice they call it a technology. It's not a company. It's a methodology. A fundamental, but many companies implement that methodology. A fundamental feature of the cloud is that everything can be delivered as a service and accessed over the internet. A service is rented rather than owned and is shared with other users. And a great example is a database. You can have a database service. No need, if you need a database, no need to have it on premises. And this is what we said. When you're talking about what services you want to get from the cloud, there's three options. One is infrastructure as a service, which means that's the most basic, just getting an actual server, a physical server. I just want a server, they give me a server, and it's got nothing on it, and I can put whatever I want on it. I just got the infrastructure. I can also get a platform, which means I maybe say I want an Apache web browser. I want certain, I don't just want an empty server. I want you to install on it certain services, certain features that I can then use to program. But I want to still program on the server, but it's going to come with installed platforms, installed development environments, ways of programming. And I'm not going to install that. You're going to install that for me. And the third, even further removed, is I don't even specify what, I'm not going to program on the computer. I just want services. I want you to provide me with information when I give requests. And I want to be able to store, I want to be able to store information on the server and retrieve information from the server through requests. How that gets done, that's the job of the cloud. So that would be requesting software as a service from the cloud. And this has lower capital costs because I don't have to, I can ask for the service today and use it for 2 weeks and then say I don't need it anymore. And I didn't have to build up a service. I didn't have to get a server and then develop all the things I want, and then I just use it for when I need it. And then we talked about multi-tenant systems, which we really talked about multi-tenant databases, where you can have one database with multiple clients using it, where they are all, each one feels like that they're the only one there. It's kind of similar to containers, but it specifically refers to databases. In other words, it's containers because they have the look and feel of independence, but they're really all sharing the same database. The key architectural issues for cloud-based software are the cloud platform to be used, whether to use a multi-tenant or a multi-instance database. You also may have to think about the scalability and resilience requirements and whether to use objects or services as the basic component of the system. All right, that is it for chapter 5. Now we'll do chapter 6.